We can now examine what happens to the pressure pattern as the angle of attack change. Starting with the low angles with an alpha of -4 degrees, the drop in pressure is the same above and below the section. There is no differential and therefore no lift. This is known as zero lift angle of attack. At 0 degrees alpha, there is a pressure decrease over the upper surface compared to free stream flow with a smaller decrease on the underside. Even at the small angles of attack between -4 degrees and 0 degrees, a positively cambered section will produce a lift. The positive pressure at the leading edge is dynamic, or in this context, stagnation pressure. As the angle of attack is increased around -4 degrees, the lift force is increased because of greater acceleration of the upper surface flow in reduced cross-sectional area of the lower stream tube. The low pressure peak moves forward as the angle of attack increases to 8 degrees. The peak is higher and further forward, and nearly all the lift is from the upper surface, but the increased frontal area means that stagnation pressure is adding to about 14 degree. Low pressure peak is well forward and the high pressure area under the wing is greater, this adding to both lift and drag. The contribution to the rearward force is due to the pressure gradient, which is in the change in pressure over the distance. The greater the pressure difference, the steeper the gradient is. As the air tries to flow from higher to lower pressure area, a favorable gradient is created, one in which the pressure is falling in the direction of the airflow, and the adverse gradient, that is one in which it is rising in the flow direction such that between the point of minimum pressure over the airfoil and trailing edge, the gradient increases with angle of attack. As the alpha reaches about 16 degree, the adverse pressure gradient is such that the air is trying to flow forward from the trailing edge, preventing the previously smooth streamlined flow from moving or following the surface of the airfoil and causing the low pressure area over the upper surface to collapse suddenly. Any pressure difference remaining is due to the pressure increase on the underside only. This condition is known as stall, described fully in later lessons. The whole surface of the airfoil contributes to lift, but the point along the chord where the lift is effectively concentrated is termed as CP, that is center of pressure. The location of center of pressure is a function of a camber and lift coefficient, which depends partly on the angle of attack as the alpha increases from 0 to 16 degree. The CP moves back along the chord. Note that the CP is at its most forward point where the lift is at its maximum just before the stall. A coefficient is a number without a unit or dimension expressing a degree of magnitude. An aerodynamic force coefficient is a common denominator for all aircraft regardless of weight, size or speed, and it is a ratio between the average aerodynamic pressure and the airstream dynamic pressure. By the definition, the lift coefficient or CL is the ratio between the lift divided by the dynamic pressure and the wing planform area. As the speed increases, assuming a constant density CD will remain constant since the drag pressure and dynamic pressure are increasing in the same proportion. We need to use the coefficient of aerodynamic force as they provide an index of the force independent of area, air density or velocity being driven from the relative pressure and the velocity distribution. There are two ways of considering the effects of pitching angle of attack on pitching moment of an aerofoil, either by measuring the changes in magnitude of lift through a moving center of pressure or by simply through a fixed aerodynamic center. You know from the previous parts of this lesson that the angle of attack increases, the CP moves forward and the magnitude of lift increases, so the vice versa. This results in changing force with a changing point of application. The aerodynamic center or AC is a fixed point on the chord line and can be defined as the point where all changes in magnitude of lift effectively takes place and point about which the pitching moment will remain constant at normal angle of attack. For the subsonic flows for Mach less than zero point 0.4, the aerodynamic center is located at 25% chord point regardless of camber thickness or angle of attack. The aerodynamic center AC is an aerodynamic reference point which is used for examining the theory of incompressible airflow, and it is most directly applicable to longitudinal stability we will discuss in later syllabus. There is a nose down pitching moment about the AC, which product of lift force and the CP, since an increase in alpha will not only increase the lift force but also shorten the lever arm as the CP moves forward within the normal flight range. With a symmetrical airfoil, the alpha of upper and lower forces are equal and symmetrically distributed with an increasing angle of attack. The upper surface force increases and the lower force decreases. A change in the magnitude of lift forces has taken place without a change in the position of center of pressure, which is a character of symmetrical airfoils. Thus, the pitching moment about this aerodynamic center will be 0 at normal alpha.